Good morning to you all.
Good morning.
Good morning, sir.
Good morning, sir. Yeah, you are welcome to this week's lecture. We have to start the lecture because it's going to be a very long lecture. So we need. So now the opportunity is available if we have more than, excuse me, if we have more than 300 candidates now, this has been large to the, we have large it to the, oh, there is a lag. Hello, can you hear me?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Yes, sir. So I have to move away from the network I was using because it's echoing and there is latency. I think it's better now.
Yes, sir. Yes, it is.
Better than the previous network.
Yes, sir.
Okay. Hello, can you still hear me?
Yes, sir.
Yes, sir.
Yes, sir. We can hear you, sir.
People, I don't know whether people are already on the YouTube channel because this is latched into the YouTube channel. That's why you are hearing the echoing. I've muted it now, but I want to be sure those who are going to the YouTube can hear me. So we are not yet up to 300. It is after 300 that we'll be moving people to YouTube. I want to be sure they will hear me because I've muted my YouTube channel now. That's why you are not hearing me twice any longer. Okay, it's already 8 o'clock. I think I have been able to remove the echoing or the retransmission by the YouTube from my own end. But I want to know whether those who are going in can still hear me, even with the way I have done it. That's number one. Number two, when you are writing your name, you write your matric number, even not just on the chat box, on the screen display here. You write your matric number first. You write your name starting with your surname. You write your name starting with your surname. And then you write your department. If I don't see you write it that way, I'm going to delete, I'm going to expunge you from my list. I'm going to expunge you from my list. Write your matric number first, your surname first, and other names, then your department. That's what I'm expecting to be displayed before me as your identity. But I can see some people, they are writing only their name and starting with first name. We delete this guy that is called Emmanuel any moment from now. The people that have not put their departments, be good enough to put it, because I will just give you 3, 4, 5 minutes to do that. If you don't do it, I should not be repeating this every lecture. I should not be repeating it. Once I see that you don't comply with this thing, I will delete you straight away. All these people, Solesi, if you don't change it very soon, I will remove you from this list. What's the name? Osejoro Dejo. I'm going to remove you any moment from now. Ewerioma David, I'm going to remove you. Ogini, I'm going to remove you. Bello, I'm going to remove you. Joshua Nwachukwu, I'm going to remove you any moment from now. Christian Adesina, I'm going to remove you any moment from now. Your matric number first, your son name, and then other name, and your department. That's what I told you several weeks ago. Ebenezer Pius, if you don't do the right thing, I'm going to remove you. Aluko Mary, I'm going to remove you. Ademuwago, I'm going to remove you. Ojachuni, I'm going to remove you. All this I'm saying for the last time. Once I go and visit where your name is being displayed as participant with me, and it is not well captured, you are going out, and I will ban you from coming in. I will just do it for my own end. I will ban you from coming in. How can I be saying the same thing every time, every day? You should grow up now. You are in the university now. All this solely say, I'm going to remove you any moment from now. Oluwatimileyin, I'm going to remove you any moment from now. Be sure of that. You can't just be giving me unnecessary things now. So we want to continue our lecture. Elumare, I'm going to remove this Elumaru, and I will ban him from coming to my lecture or her from coming to my lecture for the rest of the semester. So if you know you didn't follow my pattern, you better go and do it. Matric number first, son name, other names, then department. That's what I want. So we want to go to the lecture right away. I don't want to entertain any question for now. If you are raising up your hand, drop it. I have so much to do today. I'm not going to entertain any question for now. Let me be through with my lecture first. So anybody, I think we are audience plus now. Anybody that is not able to come in, we go to the YouTube. The YouTube is available for you to be part of the lecture. So, and I believe that is good. Now, we have 2 lectures to cover today. The network theorem. Last week, we looked at the series and parallel connection of resistors. Series and parallel connection of resistors. And we were able to investigate and work some problems. We are still going to continue like that this week. We will be allowed to, we will be bringing up some questions which we will need to solve. We're able to say that you can always go about a parallel, a series connection by tracing with your finger. If you can trace from one line to the other without meeting a junction where decision has to be taken, which path to take and which path not to take, then you are dealing with series. That means the same current is flowing through. But if you get to a junction and decision has to be made, which path to take and which path not to take, then you are dealing with a parallel connection. So on the account of that, we worked a number of problems last week during our lecture, and at the end of the day, we were able to have good understanding of that. So we want to move on this morning to network theorems. In dealing with network theorem, I expect you to write your note. I have given you some textbooks before, and I will still give you more textbooks. I will give you those textbooks again. If you don't have the soft copy, I will give you the soft copy, which I will release upon to the platform, maybe after the lecture. But more importantly, you need to have notes for this lecture. So as we are taking the lecture, you are expected to write notes. You are expected to write notes. When we are working problems, you are expected to work it in your exercise books or your notebook or your lecture notebook. And this will, when I ask questions, I expect you to work the problems inside your notebooks. So these are some of the things I believe you need to do. So as we proceed, the network theorems, there are two major network theorems, the Ohm's law and the Kirchhoff's laws. Ohm's law, you have been using it for for quite some time now. And there is no way you can work in electrical engineering space without Ohm's law, which is voltage is directly proportional to resistance. And when you are able to directly proportional to current flowing, and the constant that made this possible is R, which is resistance. So that's why you have V equals to I R or Ri. That one, you know it very well. More importantly now, with regard to the Kirchhoff's law, there are two major Kirchhoff's laws. The one that has to do with current law and the other one for voltage law. So we call one Kirchhoff current law and the other one Kirchhoff voltage law. The Kirchhoff current law is more like a nodal analysis. It's more like a nodal analysis. It states that every current or the current entry into a node and leaving a node, they are equal. Or the algebraic sum of current entering or leaving a node is zero. The algebraic sum of current entering or leaving a node is zero. Meanwhile, when we are dealing with Kirchhoff voltage law, Kirchhoff voltage law has to do with the loop or mesh. In other words, the voltage drop around a loop is equal, the algebraic sum of the voltage drop around the loop is equal to zero. The algebraic sum of voltage drop around the loop is equal to zero. So these two laws, they are very crucial to our knowledge of electrical engineering. In a number of times, we call the Kirchhoff current law the conservation of charge. Kirchhoff current law, we call it conservation of charge. While the Kirchhoff voltage law, we call it the conservation of energy. You have dealt with conservation of energy in your thermal physics and some other places when you were in secondary school. So it's still the same principle we are looking at in this place. So Kirchhoff current law is more of conservation of charge, while Kirchhoff voltage law is more of conservation of energy. So when we talk of current, it's more like a charge. Remember that when you were dealing with physics in your O level and even in your year one, we talk of Lenz's law, we talk of Biot-Savart law, and the rest of them. They are, you see where we are relating current to charges. So you can see the link between what we know before now and what we are seeing now. So there is a link between charge and current. They are directly proportional to one another. Likewise, the voltage and energy, they are directly proportional to each other. So when we are going to give a mathematical expression to the Kirchhoff current law, we have it as you have it on your screen now. in which case the algebraic sum of ingoing currents is equals to the outgoing currents any point. If you look at the number of wire entering into a node or leaving a node here, we have I1 to I5. And if you look at it closely, I1 is entering into that node, I2 is entering into that node, I3 is leaving that node, I4 is entering into the same node, I5 is leaving that node. And if you look at the expression we give, we said I in must be equal to I out. So if you look at the expression there, we have I1, which is going in. We added it to I2, which is going in. And we added it to I4, which is going in as well. And we now say they are equal to, their sum is equal to I3, which is going out, and I5, which is going out. And when we want to write it the way I described it before, the algebraic sum of current entering or leaving a node is equals to 0. That is why we have that last line. Algebraic sum of the current entering or leaving a node is equals to 0. You know that word algebraic has brought in some understanding there. It is not just sum of current entry, but algebraic sum of current entry. So we have I1 entry plus I2 entry plus I4 entry. I3 is leaving, so you say minus I3. I5 is leaving, you say minus I5. And the total of it will give you 0. If each of these has value and you add them together, algebraic family, algebraically, and it is not equal to 0, know that there is a problem somewhere. Know that there is a problem somewhere. So you have to work it again and look out for where the problem or the wrong step that you have made. Amy. Now, when we are talking of Kirchhoff current law, we said that the Kirchhoff voltage law provides an important relationship among voltage levels at around any closed loop of a network. When we are talking of the voltage current, it provides an equally important relationship among current levels at any junction. So we need to have that understanding that the voltage law provides a relationship between current levels at various levels. So Kirchhoff current law states that, I have stated this to you before, algebraic sum of the currents entry and leaving an area, leaving entry and leaving a system or junction is 0. I have already given us that. So that is, we are still providing more explanation to Kirchhoff current law here, where you have summation I in equal to summation I out. And you can see the way we work it. This is another system. That yellow blue bubble is a system. I1 is entering, I2 is leaving, I3 is leaving, I4 is entering. And if you look at the way we do it, summation of I in, those that are going in, we have I1 entry, we have I4 entry. We added the two of them. I2 is leaving, I3 is leaving. We say is equals to I out. That's the one leaving. We added I2 and I3. And you can see that 12 amps equals to 12 amps. That means that particular equation, we got the answer correct. So this is another example that you can see. You have worked with a lot of resistors before. Current is coming. Current is coming out. It's going into junction A. Maybe I should give you time to look at that. Be looking at it. I want to believe the people on the Zoom are with me out in YouTube are with us. Oh, this is good. Thank you, guys. The guys on the YouTube, I love what you are doing. Keep it up. I'm monitoring you from here. That's good of you. I can see quite a number of you. But please, let your matric number come before your surname. When you are writing next, maybe you may not be able to edit this. The guys on the YouTube, you may not be able to edit this any longer. But subsequently, let your matric number come first, followed by your surname and other names, and then department. I think Oladokun by Abdulbasit did the right thing. Likewise, Obia Sogu, you could have put your son. Adeleye did the right thing. Matric number, surname, and then mechanical engineering. Adeleye, that's good of you. The same thing, Adeyanju did the right thing. Adeyanju did the right thing. So I will capture all this at the end of the lecture as my attendance for you. So please keep it up. If there is any challenge, just send the people on YouTube, just send a WhatsApp to just send a message to either my WhatsApp or my SMS. If there's any challenge, so that we can be on the same, page. Thank you for great work that you are doing over there, guys. So look at this. Everybody draw it in your note. You may not put the blue line. I just put the blue line in order to show you how current will flow, where current is emanating from, and where current is going. So I just need you to capture the circuit. Don't put any coloration there. That color is to guide how the current will flow. Have we all drawn it? You can see the nodes. Yes, node A, B, C, and D. So you have seen the way it is worked. Node A, please, using the Kirchhoff current law, the summation of current in equals to summation of current out. Can you work that and work for node B, node C, and node D? The answers are there. Please kindly copy it before we proceed further. I'll be delaying a little further for the YouTube guys because YouTube may take some time for them to hear what I'm saying. Okay, I want to move on. So if I give you this, and I ask you to get me I3, I4, I6 and I7. Kindly walk through this for me. Get me I6, I3, I4, I6, and I7. Please, once you have done it, you should raise up your hand. The only thing is that my guys on the YouTube, they can't respond. Once you have done it, I'm monitoring here. Okay. Tessa Mavis, you didn't write your name correctly, so I will not call you. You're supposed to write your matriculation number first, your surname and other names and your department, but you didn't do that. So please drop your hand and do the correct thing. I'm waiting for those who have worked the problem. Once you have worked it, you can raise up your hand. Okpabisi Emmanuel, you have to put your department, this thing is not correct. It's not full. You don't have complete information as you have it now. Department must be part of your information. Abdullah, yes. Abdullah, can you on your camera and show us your note? I'm going to drop my own sharing right and yield it to you. So Ibrahim, okay, so I'm going to yield the floor to you. Abdullah Mohammed, on your camera. You are making noise in that place, so you can't continue like this. I will have to mute you. You can't do that. It's not allowed. You cannot answer questions under that kind of condition. So off your camera. Let somebody drop your hand. You can't answer a question from where you are. Let somebody else who is in this calm, peaceful, and noiseless place raise up his or her hand. Okay, Gbadebo, marvelous. Please, on your, yes.
Good morning, sir.
Yeah.
Yeah, the directions for I4, I7, I6, and I3 were not given, sir. For the
They
current.
are entering in, the I4 is going down. The I4 is pointing down from B to C.
Okay.
Who is making noise here now?
The one for I7 was not given, sir. I7 and I6.
I said the one for I7 is out.
Okay,
the one for I6 is pointing towards D.
Okay.
The one for I3 is pointing towards C.
Thank you, sir.
Okay. I'm waiting for you. I've indicated them. You can see them by yourself. If anybody on the YouTube has worked it, please, you can forward it to my WhatsApp. Just snap it and send it to my WhatsApp. Okay, quite a number of people have worked it. Let me start with Oyeyemi. Oyeyemi, please, can you put on your camera?
Okay, sir.
Yeah. So I will stop my own sharing right now so that you can take up the sharing of responsibility. You know the way we normally do it. So you focus
Yes,
the camera on your notebook and you teach us. Go
okay,
ahead,
sir.
please.
Sir,
You have the floor now.
So first of all,
You are not sharing your note, your note.
I'm sharing it already.
It's here to come up. Why is it not coming up? Okay. Yes,
So,
we
sir,
are seeing it now. We are seeing it now. Go ahead.
The I1 is going into the node. It is I1 is equals to I2 plus I3.
Your camera is moving away. Your camera is moving. Let it be stable.
Okay, sir.
Yes, it's better now.
I1 is equals to I2 plus I3, as I stated here. So our I1 is 10A. Our I2 is 12A. So I3 will be equals to minus 2A. That means I2 is going into this. Minus 2A implies that it's going into the node. So I pointed the direction of I3 into the node here. So it's going into the node. So for I4 now, this is I4. I2 is going into node B, while I5 is coming out of node B. So for I4, I2 will be equals to I5 plus I4. I2 is equals to 12 ampere, while I5 is equals to 8 ampere. So I4 will be equals to 12 ampere minus 8 ampere, I2 minus I5. So I4 is equals to 4 ampere. So for I6, I6 is going away from node C. I3 also is going away from node C, while I4 is going into node C. So I6 plus I3 is equals to I4. Our I6 is not given, but our I3 is 2 ampere. And I got it here, 2 ampere. So 2 ampere plus I6 is equals to I4, which is 4 ampere. So our I6 will be equals to 4 minus 2. It gave me 2 ampere. So for I7 is going out of node D. It isn't specified, but I'm assuming it's going out of node D. While I6 is going into node D, and I5 also is going into node D. So my I7 is equals to I6 plus I5. So I7 will be equals to I6 plus I5. That's 8 ampere plus 2 ampere. So my I7 is equals to 10 ampere.
Thank you. Is there any other person with opposite view to what has been presented by Oyeyemi Abdul Malik? Anyone with any other thing. I have one of my good students here. I love what he has done. Somebody has shared his own with me. He is doing it from the YouTube, and he was able to share with me. So I'm not, and the guy got the answer correct. Do we have any other person whose answer is different from what we have on board? Or if you don't understand what we have just described, let us know so that we can, in one way or the other, guide you further. Is there any person who does not really understand what we have done? Because I want to move on. But before I move on, I want to share one of the guys on the YouTube. That on the YouTube does not mean we will not be able to give them access to what others are having. So I saw that he has sent his own answer. He snapped his own note, and I'm going to share it with us now. Is Aigu Daniel, Systems Engineering. He has exactly the same answer with Oyeyemi Abdulmalik. So I'm going to be sharing his own. I forgot to put on my WhatsApp, but now I'm trying to put it on. However, okay, it has come up. The note is not showing up. I can't see his note. Okay, let's move on because we still have a long way to go. When his note comes up, I'm going to share it with us so that the people that are on the YouTube will not feel marginalized. So the answer, according to what Aigu Daniel as well asked here, the answer is very, very correct. And according to what we have done as well, the answer is very correct. So thank you, Oyeyemi, for that. Let's move on for now. So we have been able to resolve this. So let me move on from this slide. So still talking about the network theorems. Under Kirchhoff current law, there is what we call current divider rule. I want you to please take note of this, that when you have a current to be shared by a number of resistors, they don't share it equally. And there is a formula that we normally use for their sharing. If you look at what I wrote here, I said the majority of current will pass through the smallest resistor, because the more resistance you provided, the less the current that will flow through that resistance. When you give and it's just like a water. Like some of you students, you normally tell us, you will tell, I have quite a number of you, you will tell me, you will say, I will ask them, I say, okay, let's say now that you are in year 2, you want to, if we give you your certificate and say you should go, will you like? A large number of students want to just collect certificate and go. People will say, no, I need the experience. But what I'm saying is that in nature, everybody wants to pass through the path of least resistance. The same thing with current. Current wants to pass through the path of least resistance. So in this place, we have 10 ohms, we have 100 ohms, and we have 1 kilo ohms. You will see that the more current will flow in the 10 ohms because why? It has least resistance. Why least current will flow through 1 kilo ohms? Because it has higher resistance or highest resistance. So we must have that at the back of our mind. And so we have a way of solving that out. So that is about that. So you can talk, maybe I should just leave this for another 1 minute so that you can copy it. Current divider rule. I'll soon be moving. So when we are talking of current divider rule, this is a typical way of working it. Your R total, because if you look at this diagram, circuit diagram, the R1 and R2, they are in parallel. Why are they in parallel? The current flowing from IT, it will have to make decision when it gets to that point that looks like a junction, whether to flow towards I1 or to flow towards I2. And I've told you in the previous lecture that when decision has to be made, then it is a parallel connection. So when that occurs, your R total will be product of the total R plus over sum of the total R. Product of the total R over sum of the total R. Don't forget this formula. Let it guide you in your current divider rule, because you are going to meet quite a number of areas that you need to apply this particular rule. So please take note of it. Now, when I want to work and you can see my RT here in the diagram, you can see my RT pointing towards R1, R2 in parallel. Now, my I1, current resistor R1, the formula is, as you have seen it, R total over R1, because you are looking for current in I1. So it will be R total over R1 times total current. That is current divider rule. However, when you go further, remember that our R total is product of R. Why I'm not saying R1, R2 is that it can be 4 resistors in parallel. It can be 10 resistors in parallel. You must do the product. That's why I don't want to say R1, R2, because you may miss situations where we will have more resistance, more numbers of resistors than 2. So on the account of that, the product of all of them over the sum of all of them. So when you do that, we put it over R1 times IT. And you can see R1, we cancel out R1. So you will have R2 over R1 plus R2 IT. Do you get what I've said here? Then for I2, it will be the reciprocal, because there are 2 of them this time around. So it will just be R1 over R1 plus R2 times IT. So please copy this. This is divider rule. You will need it quite a lot in the course of this work. Finally, copy it fast so that we can proceed and move forward. I want to move forward. So I'm moving now. We have to move. So next, as I told you last week, I may ask for your note any moment from now. And I will be asking for it based on department. I may ask your class rep to get me all your notes and bring it to campus one day. So you have to have your note complete. So looking at this, another thing I want to introduce you to is that if you look at this, I'm not entertaining question, I'll write all your questions down. When I have time, I will ask you to give your question, because I don't want to be delayed unnecessarily. I want to cover quite a lot of things because we have a long way to go. Now, if you look at the circuit diagram, the first one on top, you see that blue highlight was given, and it is written single node. That is, if you bring all those 3 points together, they are at the same potential. Why? Because there is no resistance, no resistor connected to any of those branches. So on the account of that, they are all at the same node. So you can't label one A, the other one B, the other one C. They belong to one node because there is no resistor there. Please take note of that. The only reason why you can label it A is because of the resistor going down. For the resistor going down, for the other one B, for the resistor going down from the other C. But when you are looking at the VA, it will be equal to VB, it will be equal to VC. Please take note of that. Even though the current will not be the same, I must tell you that the current that will flow in each of those branches will be determined by the resistor that is drawing the current. Then the same thing is applicable. If you look at the circuit diagram under, you can form the total resistance as it is shown by the right-hand side. And then you can see the current flowing in each of them. And you can use the current divider method to know I1, to know I2, to know I3, and other I, as many as you will have in your, you will just use this method to get these currents. Because you can see I1, I2, I3, up to IN. Now, somebody has thought, when Oyeyemi was giving us the description or the explanation on the problem I asked you to solve, he had already given this. So I don't need to overflow it again. This is called sign convention for currents at the node. When you have negative, that means it's pointing away from the direction that you have chosen before then. Please take note. But for the convention, when you are drawing this thing, current are positive when they are entering into the node. That's our belief. But by the time you do your calculation, it will be otherwise, like Oyeyemi showed to us. I gave him a direction that current should flow, but by the time he worked the problem, he found out that the current cannot flow in that direction because the answer is getting is negative. So he refers the direction of the current. The same thing here, it is our conventional belief, which we stand by and we stand for, that current that flows into the node, we take them as positive. The current that flow out, we take them as negative. Please take note of that. Take note of that. It's very crucial so that you don't just do things haphazardly. I have treated this before, so there's no need for that. So if I give you this, oh, sorry. Look at this as well. If I say find this current in each section in this circuit, please kindly draw this circuit. Draw this circuit right away. That's why I said we have a lot to do today. Whether we are in the physical classroom or we are in the virtual classroom as we are, I believe that we can still make serious progress. I don't expect you to perform less than our previous students who had physical classroom. And so please, you have I have a demand from you that you will not take this lecture for granted. You will work the same way if you had been in classroom with me face to face. And that's why I want to engage you by asking that you work problems. Not just for me to come here and dump the notes on you. And that's why I don't need anybody to ask me questions. And that's why I'm making students, these are problems I solved, but I'm making students to solve it so that one way or the other, you will see that it's something any of you could solve. Once I give you the rudimentary steps that you need to take, there is nothing I am doing that you cannot do. what I give you the step. That's the joy of engineering. Just give me the procedure of doing it, and I will try my hand on it. And I assure you that I shouldn't get anything less than what we have gotten. So please, asking question now should be towards the end, because I want us to really move. And we are not meeting physically, should not in any way be a barrier our getting it right. So I'm waiting. I have 2 more minutes that I'm giving for this problem to be solved, because we have already spent 1.5 minutes now by my time. So the current entry into the node is positive. The current leaving the node, we take it as negative. From the sign convention I gave to you earlier on, maybe I should flash it again. This is the convention that I gave to you. Current entry into a node is positive. Current leaving the node is negative. Don't forget this. Let it guide you in your working this problem. My remaining 2 minutes is remaining 1 minute now. By now, somebody should have finished this, solving this, monitoring the guys online as well on YouTube. I've not seen anybody tell me. I don't need anybody to talk. Don't talk on this platform except I give you opportunity. And that will be towards the end, except you work a problem and you want you to explain it. Guys on the YouTube, please, if you are through with it, just send it to my WhatsApp. I will display it as well. The only thing is that I will be the one to help you speak to it. You will not be able to speak to your own. But if you finish ahead, please just post it on my WhatsApp. You should not in any way have less privilege than the people who were able to come in ahead of you onto the YouTube. I'll be onto the Zoom link. My 4 minutes has been exhausted, but I will give you 2 more minutes. Because if you can get some of these things, okay. Oyeyemi has raised up his hand again. I want to believe where you are is very quiet and there is no interruption, interruptive noise from your surrounding, because the other time we had noise problem. And number 2, let your camera be stable so that we don't waste too much time in your explanation. I have seen that Oyeyemi has finished. It is ready to give us its own solution. And if the guys on the YouTube are finished, I'm monitoring you also. So I will drop my sharing right for Oyeyemi to share his own notebook with us. Thank you. Also, Ogunleke has finished, but Ogunleke, wait, let's see that of Oyeyemi first. Focus it on your note. You see, you are focusing on your ceiling. Oh, several people have finished it. Abolarinwa has finished it as well. This is good. Who else can I see? So please watch what Oyeyemi wants to display. If there's anything we need to correct, I will wait for you. Ariori Ibrahim as well has finished. Okay.
So,
We can see your note now, Oyeyemi.
so at node A, 1A is going out of node A, while 3 ampere is going into node A, and IAB is coming out of node A. So as I said before, I in is equals to I out. So 3A is going into node A. 3 ampere is going into node A. So 3A is equals to IAB coming out of node A and 1A coming out of node A. So 3AB is equals to IAB plus 1A. So our IAB is equals to 2 ampere. So at node B, IAB is going into node B and 3 ampere is going into node B, while IBC is coming out of node B. So IAB plus 3A is equals to IBC. IAB plus 3A. IAB plus 3A is equals to IBC. So our IAB is 2A as you have gotten here, plus 3A is equals to IBC. So our IBC is equals to 5 ampere. So at node C, IBC is coming into node C, while 4 ampere and 4 ampere also is coming to node C, while ICD is going out of node C. So IBC plus 4A plus ICD is equals to 0. As you have said before, the algebraic sum is equals to 0. So 5 ampere, that's IBC. 5 ampere going into node A. 4 ampere is positive because going into node C, 4 ampere also is positive because it's going into node C. While ICD is negative because it's going out of node C. So 5 ampere plus 4 ampere minus ICD is equals to 0. So our ICD is equals to 9 ampere. So at node D, ICD is going into node D. IDE also is going into node D. While 8 ampere is coming out of node D. So our ICD is equals to 8A plus IDE. So our IDE is equals to our IDE is equals to ICD minus 8A. ID is now equals to 9A minus 8A. Our ID is now equals to 1 ampere. That's
Thank you. Thank you. Let me give Ariori Ibrahim. Elumaro, I'm coming to your question, but is Ariori still with us?
Yes, sir.
Okay, let me share your notebook with us, please. You have the sharing right now. Okay, if you cannot do that, Aluko Mary, do you want to share your own note? Aluko Mary.
I want to.
We can't hear you clearly. We can't hear you. Your network is bad. Okafo, why is your hand up? Okafo Chibueze.
Yes, sir. So I want to ask one question. Instead of doing like that,
Don't worry. Don't worry.
No. I want to say the answer, but I don't know whether it's correct. Can we do?
Go ahead. Let me see it.
Can we do?
Let me see your note. Let me see your note. I'm coming back to Oyeyemi Elumaro. I'm seeing what you sent to me that you did not understand. But let's see those who understand so that we will explain it again. So, Okafo Chibueze, do you want to display your note for us?
Sir, no, I don't want to display my notes, but I want to say the answer.
Then please drop your hand and close the mic. Abi, mute the mic. I've had your question that you want to know certain things. So please close or mute. Mute yourself, brother. Now, Oyeyemi, display that answer again, your notebook again.
okay, sir.
Elumaro said he didn't understand what we are doing, and I want him to, and I appreciate that kind of a fellow. So we want to further explain things to him. So please hear your note again. Yeah. So Elumaro, I want to believe you are listening. If you know you are listening, can you send me a chat again, the way you sent the first one? Elumaro, can you send a chat before we start this? So that we'll not be just speaking. Okay, Elumaro has sent it. Said it's listening. Good of you. Okay. Please let your camera be stable. Oyeyemi, Oyeyemi. Don't be
Yes, sir.
flashing. Yes. Now, explain all over again. Elumaro is here.
Okay, so the thing is that, as was said before in the slide, the total amount of current going into a node is equals to the total amount of current coming out of the node. As you can see here now, this 3 ampere is going into node A. 1 ampere is coming out of node A, and IAB is also coming out of node A. 3 ampere is going into node A, so it's positive. It's positive. It's positive. 3 ampere is positive. 3 ampere is positive. 1 ampere is going out of node A, so it will be negative. It will be minus 1 ampere. While IAB is going out of node A, it will also be negative, minus IAB. As was said before, the algebraic sum of all the currents in a node is equals to 0. So IAB will be equals to what? 2A minus IAB equals 0. IAB equals 2 ampere. So that's how I got 2 ampere for IAB. That's how I got 2 ampere. And as you can see, this is node B. This is node B. IAB is 2 ampere. It's going into node B. 3A also is going into node B. So the two of them are positive. These two, IAB and 3 ampere, the two of them, they are positive. So 2A plus 3A. Why IBC, as you can see, the direction of the current is coming out of node B. So it will be negative, minus IBC. The algebraic sum will be equals to 0. So if you calculate this, you get IBC equals to 5 ampere. So that's how I got my IBC. As you can see, the node C, IBC is coming to node C. So IBC is positive. 4 ampere is going into node C. It is also positive. So 5 ampere plus 4 ampere. Why this? If you can see this ICD, see the direction of the current is going out of node C. So our ICD will be negative, minus ICD. The algebraic sum give us 0. So if you calculate it, your ICD will be equals to 9 ampere. And so at node D, ICD is going into node D. So that makes it positive. So ICD going into node D, it will be 9 ampere. As you know, our ICD is 9 ampere. Why 8 ampere is coming out of node D, it will be negative, minus 8 ampere. And this IDE is going out of node D. IDE is going out of node D, so it will be negative also. As you can see, the direction is going out, so it will be negative, minus IDE is equals to algebraic sum equals 0. So our IDE will be equals to 1 ampere. So that's how I got my answer.
Thank you. Thank you. I believe the Elumaru, you are best informed now. Okay. Thank you. You have responded. Thank you for that. So I appreciate you for that feedback that you didn't understand and you want us to take it all over again. Thank you. Oyeyemi, I appreciate you as well. You can see that it's not a rocket science, that if you listen, what I give to you, once I give you the tool that you need to use, you can do this. So I don't want anybody to feel apprehensive or anxious that will I be able to understand it. And that's why I am not showing my own working. I'm showing you the way your classmate. I have never met Oyeyemi one-on-one. I've never met what's the name of this, my friend, those who answered questions for me last week. Daniel, I've never met him one-on-one. So it is on this platform that I've been seeing all of you, and they are keen into what I'm teaching them. You as well, if you're keen into it, if you don't understand, please call us back. That's why I said, the only thing I would like is that just send a chat. I don't understand what is going on because I'm monitoring all the platforms so that everybody can be carried along. We don't want to leave anybody behind. So please, I need your cooperation. So this is another problem. But because we have solved that other one, I may not bother you with this. But let me quickly raise a point of observation. When I gave you a problem before now, that problem that has blue highlight, this problem, I didn't give the direction of the current, this particular problem. I purposely did not. But I remember that I should have given it because I'm just starting with you. But if you look at this now, I did not give the direction. I didn't give direction of current here, just like that one. But somebody called me, so I had to give that time. But now, let me tell you why I didn't give direction, especially to this particular question. I want you to use your initiative. Even if you put the direction in the wrong way, your answer will tell you that it is wrong. Because if instead of getting your answer as positive, you like I3, if I point I3 towards node A, if the answer is, if at the end of the day we work it out and the answer is minus something, I know that my direction that I assumed was wrong. So you are allowed, an examiner may not give you direction to the current, but you are allowed to choose the direction by yourself. I have had some students in the past, they will put all of them, they have this mindset, and they will put every current that I don't give direction, they will put it out of the node. They will put it from one node to the other. They normally like to follow right hand. They will say they will take all their arrow towards right. That is, if somebody wants to assign arrow to the resistor between A and C now, he will point it towards C. If you want to assign resistor direction for the resistor I6, he would point it towards D. So there are people like that. But one thing I need you to understand is that whether you point it towards right or towards left, your answer will tell you whether you are correct or not. And that's why I want us to work this problem before I move on. So let's put our hands to this problem. Write the current in each of the section without, I will not supply you the direction, give yourself direction and go ahead and work it. You have 5 minutes for this. It shouldn't be up to 5 minutes with what we have done before, but I just want 5 minutes so that we can. But if you finish before 5 minutes, please don't interrupt my lecture. If you need anything, you send it by chat. I've said it before. Don't interrupt my lecture for any reason, please. Any information you want, send it by chat or by WhatsApp. You can see Elumaro did not call me. He did not interrupt lecture. He just sent a message and I responded to his message. So if you have any challenge, just send a WhatsApp. Don't interrupt the lecture. Okay, somebody said we have solved it before, so we can move on. It's because I want you to put the direction to it. However, since we have solved it before, let me move on then. Okay. This is another problem that you can solve. Please jot this down. Jot this down in your note. This is very simple to solve. So with this now, I have been able to take you through several of our problems that we have with Kirchhoff current law. I want to move on to current Kirchhoff voltage law, which is just almost the same thing, but now you are dealing with voltage. So just like we have said, algebraic sum of the current of the voltage drops around any loop is equals to 0. And you can see it here. Just like I gave you the sign convention for current flow to a junction. In the loop as well, we have some convention. The first convention we have is that voltage drops are positive in the direction of the set loop current. That is, if you have current flowing in a particular direction, voltage drops are positive in that same direction. Whereas if your loop current, what we call loop current is what you are seeing in your diagram here by your right. That curved arrow with I1 inside, and that curved arrow with I2 inside, they are what we call loop current. Because there are two loops here. The first loop is the loop made up of V and R1. The second loop is made up of R1 and R2. So take note of that, please. Loop 1 is made up of V and R1, and loop 2 is made up of R1 and R2. And we label our current in the loop according to the loop number. So that's why you have I1 inside loop 1 and I2 inside loop 2. So what I'm saying is that the current drop, the voltage drop are positive if you are following the direction of the flow of current. But if you are following the opposite direction of the flow of current in the branches, then your loop will be, your voltage drop will be negative. Your voltage drop will be negative. Remember, during the current, we said when the current is entering into a node, we take it as positive. When it is leaving the node, we take it as negative. Now we are saying for loop, when your loop current is following the direction of the branch current in the circuit, then you call the voltage drop positive. But when it is the current is flowing in the branch on the right, to the right, and your loop is taking the loop to the left, is defining its path to the left, then it is opposing it, and on the account of that, you take your voltage drop as negative. Then the third thing that you must know is that voltage source is positive if current flows out of positive side. If your current is flowing out of the positive side, like the upper part of this particular V, if current is flowing out of it, you say that your current flow is positive. I mean, your voltage source is positive. But if your voltage is flowing through the negative arm of your voltage, then you say that the voltage source is negative. So it's complicated, but I just need you to copy this, follow it, because we are going to go into some questions that you will need to make use of it. Take care of those sign conventions. They are very, very crucial. If you have question, put it on the chat. I've said that I'm not going to entertain any question for now. But if you want to answer anything, you are the only one that will raise up your hands. I believe you have written this sign convention down, because I want to move to the next slide. Okay, I will wait a little further. Jacob Righteous said he has not copied. Okay. Please make it fast so that we can go to the next slide. You can see that we started on dot of 8. And we have not gone far. Even though we have spent more than 1 hour, about 1 hour, 15 minutes. Please take note, these are the tools you need for the rest of your career as an engineer. So take note of this sign convention. You will meet them for the rest of your life as a practicing engineer. Don't be afraid. All these things are easy to understand. You will permit me to move to the next slide now. I want to believe everybody has written. Okay. The guy that said he has not written has written. Thank you, my boy. So let's move to the next slide. Okay, we are on the next slide now. I want to start with voltage divider method. I've shown you the current divider. Current divider is more like an inverse proportion. Maybe I should call it that. I didn't mention that at the other side, but it's more like an inverse proportion. What do I mean by inverse proportion? The current may be, if the resistor is high, low, the current in that resistor will be high. That's inverse. If the resistor is high, the current flowing in that resistance, in that resistor will be low. You can get, I believe you get what I'm saying. But in the case of voltage divider, the vote is direct proportion. The voltage that we drop across the resistor depends on the resistance there. If the resistance is high, the voltage that we drop there will be high. If the current, if the resistor is low, the voltage that we drop in that branch will be low. Take note, let me repeat myself. For current divider method, it's more like an inverse. In which case, if the resistor is high, the current that we drop there will be low. If the resistor is high, is low, the current that we flow through it, rather, the current that we flow through it will be high. If the resistor is high, the current that we flow through it will be low. Take note of it. Low resistance, high current flow. High resistance, no current flow. Take note. But in the case of voltage divider method, low resistance, low voltage. High resistance, high voltage. Thank you. So in looking at this, you want to look at the current that will flow in that loop, I1. We have V over R1 plus R2. Then, what is the voltage that we drop at R1 alone? V1 is equal to, you can see the V1 there, is equal to I1 R1. And we have already calculated I1 to be, the value of I1 is there. So you can now write it this way. You can see now that R1 over R1 plus R2 is the one that is multiplying the total voltage. So if you look at the resistance is 2 ohms. The voltage that drop across it is what? 2 volts. If you look at V2, sorry, I wrote V1 again. I was to write V2 for the second one. Please write V2 in your note. I will need to correct that. Write V2 in your note. It's not V1. It's when I was doing cut and paste of my work. So instead of V1, that one is V2. And you can see for V2, the resistance is 3K and the voltage is 3 volts. So the drop across a resistance is determined by the voltage flowing. The higher the resistance, the higher the voltage drop. The lower the resistance, the lower the voltage drop. If it does not work like that, if you work a problem and you are having that challenge, know that you have made mistakes somewhere. So quickly look at it all over again and correct yourself. So this is still the same. Can I ask you to work this for me? Please try your hand on this to get me the voltage drop across R1, R2, and R3. R1, R2, and R3. Remember what I gave to you about convention. The sign convention is here. Let me report it again. Voltage drop across a positive in the direction of this loop current. And voltage drop negative when it is opposing the loop current. Voltage source positive if current flows out of the positive terminal. Voltage source is negative if current flows into the positive terminal. If it flows into the positive terminal, it is negative. That voltage is negative. If flowing out of the positive terminal, it is positive. If the voltage drop across a resistor is flowing in the same direction as the branch current, it is positive. If it is flowing in the opposite direction to the branch current, it is negative. Please take note of those 4 items, and I return you back to the problem. So let's give this another 5 minutes. Guys, I believe we have not worked this before. My boys that are helping me to check whether we have worked the problem before. I believe we have not worked this before. So, okay, so let's work it right away. Get me the current voltage drop at R1. Get me the voltage drop at R2. Get me the voltage drop at R3. Voltage drop at R1, voltage drop at R2 and R3.
So there's no R3.
R3 is the one linking the two of them at the middle of the 2 loops. Have you seen it? I've told you, always send me message.
Yes, sir.
Don't let us make this class route. How do we know where the current is flowing? Because I didn't show that. Okay, that's a good question. One of my guys just asked me on the chat box. That's Abolade Elijah from Systems Engineering. He said, how do we know where the current is flowing? Now, like the problem I give to you now I've told you that current direction, you are at liberty. If I do not give it to you, you are at the liberty to follow your own direction. I've told you that before, and I'm repeating it again. But when you see a positive side of the battery, just like as I've shown you before, that when a current is flowing into the positive side of the battery, it's called negative flow of current. But when current is flowing out of the positive terminal of the battery, it's called positive flow of current. The same way, if you put your battery in your radio, you know the way it does now, or you put battery in your recharge, your lamp, or you put battery in your dad's car, you know the way you should connect it. And the battery is expected to give energy out. But when it's now the one taking energy in, that's why we say it is now negative. But when it's giving energy out, it's his normal responsibility. So we call it positive. So like this problem now, if I were you, the positive side, since I didn't give you direction, if I were you, I will give myself direction. I will give positive side pointing out so that I can say my current is positive, that it is the voltage V1 that is giving current out. And when I get to the place at that junction where I need to make decision, because current from the battery is flowing in to that junction, I can then say the two of them should flow out. After all, if I'm wrong, the only thing that will change it is that I will still get the same value. The only thing that will change is my direction. So you can give it positive out of the two of them to be out of that junction. And that means by the time you are getting to V2 on the other side, you are now feeding in current into the battery. So in this case, the current that is entering into it, what did we say? We said it will be negative. Because the work of the battery is to give out energy, not to accept energy. That's the sign convention I gave to you. So let's go ahead and work this. And let's see what we are going to get out of it. Once you have done it, please raise up your hand so that I can take it up from there. So can we, somebody else is asking, can the voltage divider method also be worked for this? There's no problem with it. You can go ahead with voltage divider method. You are free to use any method that suits you. But because it is voltage, Kirchhoff voltage law, you will always have to deal with loop. Because you must always follow your first principle. The first principle is what we have here, that you will have, this is your first principle, that the voltage in your this thing will be VJ. You will have to do algebraic sum of all the voltage drop inside your loops. You have to add them together. So you still have to write those loop equations. Here now you will have two loop equations to write. Then you can now use any other method that you want. But for Kirchhoff voltage law, you must write your loop equation. I see that tedious. Nobody has finished. Unlike the current. Okay. I believe I only want those who have finished to raise up their hands. If you have questions, chat with me on the chat box. Speak with me through the chat box. Just put your question there. It's only those who are true and ready to share their own experience with us that is permitted to raise up their hands. If you know you have finished working the problem, you have raised up your hand, I'm going to be calling you. Vincent Chukwunonso, I want to believe you have finished working the problem.
Yes, sir.
Put up your camera. Activate your camera and put it on your work, on your notebook. I'm going to stop sharing so that you can have the right to share. You have the responsibility to share now.
So this is the circuit.
You have not been able to see your screen.
That is my screen. My
You
screen
have
is
not been
sharing.
able to see your screen. Share your screen with us. Somebody said he doesn't understand voltage divider method. Don't worry. We'll come back to all these things that you are asking. Let me just, you should have said it long before now. Chukwunonso, we can see a whiteboard. Are you using your phone? We can't see what you want to share with us.
So I see my screen.
We can't. Ayodele, we will look at voltage divider method later. Let us share this problem together. Is there any other person who has worked it? Vincent Chukwunonso, maybe the network around your area is poor.
So we can see the screen.
And me, I cannot see it too.
I cannot see it.
Chukwunonso,
Sir,
share your screen now.
sir, I've shared it already.
So you need to pin the screen.
The other people have been sharing with me since the commencement of the. Then drop it. Let somebody else who has worked share their own. I think it's either I'm having challenges with my own. Maybe my network is poor. But I need to see it because I will have to guide you. Drop it and share again, Vincent. Drop it and share it again. Your camera is closed now. How can you share anything without your camera being on? Chukwunonso, your camera is off.
I know.
There's no way you can share without your camera being on.
Is it showing now?
I'm not seeing yet. Let me check the people online. Maybe some of them have done it.
Is that actually my screen?
You can see your screen.
Please, I don't want anybody to talk. If you talk without my permission, I will throw you out of here. Uchechukwu, can you share your screen? There's no way you will share that I will not see now.
Yes, sir.
Go ahead and share your screen, please.
Okay.
Uchechukwu, Ebubechukwu. Who is telling me that he's seen the screen?
Okay, sir. Can you see it, sir?
I can see.
Okay. I had to rename
But
some.
you have several things.
Yeah, the right side. Sorry about that. I had to divide the book.
Okay.
Okay. So I had to rename some
properly now.
Okay, sir. Sorry, I will do that
I can't see your notebook. Oh.
Can you see it now?
I can't see your notebook.
Oh.
I can see the whole of your gallery.
Oh, sorry about that. I'm a bit confused here.
It's the whole of your gallery. You have been snapping my notes. Don't worry, that's a good one.
My God.
It's the gallery I'm seeing. I'm not seeing your note.
I want to share the screen, but I'm a bit
That's
confused.
very intelligent of you.
I'm trying to share it, but I'm a bit confused.
Your notebook where you solve the problem. All these one are the notes that you have copied from me.
Yes, I'm trying to. Oh, I have to snap it.
If you want to snap it, no problem. I tell what I'm seeing here are the notes that you took from
I'm
me.
very sorry. I'm a bit confused on how to share. Okay, I've changed it. Can you see my screen now?
No, just focus your camera. Focus your camera on your notebook.
Can you see it now? Can you see it now?
Focus your camera on your notebook if you cannot, so that I can speak.
Okay, can you see it now?
It's not coming up yet.
Okay.
Why? What's going on? Students, some students are saying that they can see your screen, but for me, I can't see it. And I need to see it so that I can be able to guide as you are giving the answer to those questions, to the Chukwunonso, please focus it on your note. Chukunozo, let somebody else who has solved this problem share the note. Oyeyemi, you have shared note with me severally on this platform. If you have done it, can you share your own?
I'm not done it, sir.
Oyeyemi,
I'm not done it, sir.
you have done it.
I'm still doing it, sir.
Okay.
I was logged out. I was logged out. I just logged in again.
Okay. There's another guy that is always Daniel. If you have worked the problem, let me see your answer. I guru, if I'm correct. Daniel, if you have solved the problem, let me know, because you have been sharing with me for some times now. See that difficult? That is taking too many. Ariori, do you want to try?
Okay, sir. Okay. Okay, sir. Can you see my screen? Can you see the screen? Okay,
Yes.
sir. This is the solution for the this I'm coming.
No problem.
Okay, sir. This is my solution for this current. So I have Kirchhoff rule. For the formula for Kirchhoff rule is that summation of voltage drop or the voltage in a particular loop is equals to 0. Now, I first apply Kirchhoff current law at this point. I make current 1 goes in this direction, current 2 go in this direction, and current 3 go in that direction, so that I1 plus I3 plus I2 will be equals to 0. That's the Kirchhoff's current law. That's this, and this is my equation 1. At this loop, that is loop 1, I have 5 volts, which is positive. I'm going in the clockwise direction. I have 5 volts. This one is plus 1 kilovolts, because I'm going in the opposite direction of the current, and the sign convention will be positive. So this will be what? 1000 ohms times the current I1, which is 1000 I1, then minus 3000 I3. That's the total voltage on this loop, and this equals to 0. And that equals to 0, which I use it to derive this equation that minus 1000 I plus 3000 I3 equals to 5. That's my equation 2. On this second loop, I have this, which is plus 3000 I3, because I'm opposing the current which is doing the voltage drop. If I'm opposing the current doing the voltage drop, which means I'm rising in the voltage, so the sign will be positive. So plus 3000 I3, then minus 2000 I2, then minus 1 volt. This is 1 volt, because I'm opposing the direction of the voltage supply, it now be minus 1 volt. And that is the total voltage on this loop, and that equals to 0. I get my equation 3 from there. Solving the 3 equations simultaneously, I get my I1 to be equals to minus 2 milliamps, which means my direction of the current here is incorrect. I'm supposed to move the current in the opposite direction. I get my current 2 to be equals to 1 milliamps and my I3 to be equals to 1 milliamps, solving it simultaneously.
Yeah, guys, can you see any problem with this? Does anybody get any answer? Ariore, still put it up. Put it up. Does anybody get any answer different from this? Killer and Co. Do you have an answer different from this? Does any, okay, David Olasubomi said he doesn't understand. Ariori, explain it again for one more time. Observing all the rules that we have put. I like your camera is very focused. Another person said, does it mean if you get a negative current? Let me check that guy. Let me respond to some of these things. Does it mean if you get this, Emmanuel Oyibo, does it mean if you get a negative current, the work is wrong? No. If you get a negative current, it means your direction of flow of current is supposed to be reversed. That means the direction of flow of your current needs to be reversed. So thank you. Ariori, please go through it again for the sake of my friend that said he didn't understand. I need you to go through it once more.
Okay. Yeah. Before I proceed, let me first share this.
Sorry, Ariori, let me answer this question. Somebody put here, he said, I can't see it. I thought moving, oh God. I thought that when moving from a negative terminal to positive terminal, the voltage is negative and vice versa. That's this guy, I can't see your name, that Anon Yai, David. No, what we said is that if the current is flowing into the positive terminal of a battery or of your voltage source, if the current is flowing into the terminal, then you take the current as negative. Because normally battery is supposed to supply current. It's not to absorb current. So you take it as negative. But when the current is flowing out of the positive terminal of your battery, then you take it as positive. That's what we said. That's what we said. When current is flowing into the terminal, positive terminal of your battery or voltage source, we take it as negative. But when current is flowing out of the positive terminal of your battery or your voltage source, you take it as positive. That's the convention that we shared with you. Ariori, please run through it from the beginning again. I can see that you put positive, negative in some places. Explain it to the others so that they will know why. Where I didn't put positive, negative, you are put in some of them. So explain it from there. You have the floor.
Okay. The principle basically is this. In a voltage source, the current will run, when current is running through the voltage source, the current running through the voltage source, it goes out from the positive and goes in through the negative. While for the resistance, when current is flowing like this, then it is going from through the positive and coming out from the negative, because power is lost on the resistor and the power is given out by the voltage source. So coming here, we can see that I3 is coming in this direction. automatically this place will be our positive and negative. I1 is coming like this. This will be our positive and this will be our negatives because currents enter through resistors from the positive side and come out from the negative side. So the same thing as our I3, this will be our I3 coming here through the resistor. So this part will be our positive, this part will be our negative. I2 coming like this part will be our positive and this part will be our negative. Now, when you are moving from positive to negative, your sign convention is minus. When you are moving from negative to positive, your sign convention is plus. Now, let's now solve the question. Looking at this is my loop 1. I want to move in the clockwise direction.
Label it as I1, please. Label
This
it
one
as I1 and I2.
And this one is my loop 2. So in my loop 1, I am moving in clockwise direction. So I'm moving from negative to positive part of the voltage source. So that's my plus 5 volts. Then I am also moving from negative to positive part of the resistor. Then it will also be plus 1 kilo ohms, which is 1000 ohms times the current passing through it, because my V equals to IR. It now be plus 1000 I1. And also, this time around, I'm moving from positive to negative. So my sign convention will be negative. So which should be equals to what? Minus 3 kilo ohms here, which is 3000 times the current I3, which is this, is equals to 0 because no more resistor or voltage source here. So that is my KVL for this loop. For the second loop, the same way, I want to move in the clockwise direction. Now, this time around, negative to positive is what? Plus 3000 I3. Then, positive to negative, it now be minus 2000 times I2, which is this. Then, from positive to negative, it now be minus 1 volt equals to 0. And so we have 3 unknown. We don't know I1, we don't know I2, we don't know I3. And we already have 2 equations on ground. We have this equation, we also have this equation. We need the third equation. Third equation, we can get it by considering this node and KCL such that I1 plus I2, I3 plus I2, total current leaving this node is equals to 0. So solving this question, so we have 3 equations and 3 unknowns now. So solving it simultaneously, you'll be having I1 equals to minus 2 times 10 to the power minus 3 ampere, I2 equals to 1 times 10 to the power minus 3 ampere, I3 equals to 1 times 10 to the power minus 3 ampere. Getting negative in the I1 means normally the current supposed to go in this direction, not the direction I assumed, but it's supposed to go in this direction. And that is my final answer.
Thank you. Thank you. You see now that I didn't want to argue with him because if you look at the source of his voltage, the highest one is the 5 volts, but he's pointing an arrow from current into the positive terminal, which will make it to be negative. And by the time he worked his problem, that situation reversed itself by itself. So I need you to take note of that. Don't worry about the direction you have taken with your current. It will always reverse itself when it is not a correct direction. Now, number 2 thing I need you to capture from what we have done is that always make your loop current to be in the clockwise direction. Let it follow the direction of the clock. If you are using an analog clock or watch, just like I do, you will see that the way the arm of your minute, second, and hour is moving with your respect to your wristwatch is the same direction you should maintain. Thank you. I think I need to pass that information. And that's the direction he followed. So thank you, Ariori, for that. We appreciate you. Now we want to move on. If you have any other question, please put it on the chat box. Okay, if there's none for now, I will soon be closing the meeting, though we still have some few minutes. I would like us to even follow it. So that's about Kirchhoff voltage law. We have seen the way to work it there. So that's exactly what I tried there. So we are with that, we are through with Kirchhoff laws. I want to quickly move to the nodal analysis. I may not be able to finish this today because this particular one is for week 3 and week 4. We are doing well if we are able to finish. We have finished Kirchhoff laws. Maybe I should just make a little introduction to this and we close because I won't want to take too much of your time, knowing that some of you may have another lecture after this one. The next set of things that we want to look at is nodal and mesh analysis of circuit. We have laid the foundation for us. We have laid the foundation by telling you the device laws. We have told you that Ohm's law is important. We have been able to go through the Kirchhoff laws, which are rudimentary to your knowledge of electrical engineering study. And as a build-up on the Kirchhoff laws, we have what we call mesh and nodal analysis, which is what we are going to be looking at in a few, by the grace of God, from next week lecture. From next week lecture, we'll be looking at it by the special grace of God. However, the nodal analysis will most of the time be working alongside with what you already know in respect of the current law. Because we have told you that we are going to make use of, and the nodes, you will have voltages. We will label each of the nodes in a manner that it will permit you to be able to work the problem with ease. So the nodal analysis provides a general procedure for analyzing circuit using node voltages. We'll be using node voltages as the circuit variable. And we will be choosing some node voltage instead of element voltage as circuit variables. But at this point, I want to share with you your first assignment, which we call problem set 1. Problem set 1. I'm going to give it to you today. I'm going to share it on the platform, on the chat box, so that you can pick it up. But let me just show a little bit of it. So we'll start with nodal analysis and mesh analysis next week. So you are going to work on this because we were thinking that our lecture, when we started our lecture, this assignment is long overdue now. You're supposed to have submitted it by last week, Monday, but I will allow you to submit it by this These are the problems that you are going to solve here. We were waiting for us to cover Kirchhoff voltage and current, which we have done. So these are the problems that you are going to solve. So I'm going to share it with you now on the chat box. And there will still be a number of people have been asking me about the lab. The lab component, we are still developing our mode of operation. And our mode of operation, no matter how it takes or what it takes, the time it takes, the major thing is that we will make it so flexible that it will not be too much of pressure on you, but you will have to come to campus on the day of such lectures, of just such practical. You will have to be on campus. That's the only thing I can tell you for now. But beyond that, I may not have much information for you. That's about that. That's about that. But I'm sharing this now on the WhatsApp, on the chat box, and probably the people that are using what's the name? The people that are on the YouTube channel, they may not be able to download this, but we will make it available on the class reps, this thing as well. We'll make it available on the class reps chat. So just give me a minute to share this. So now that we have covered a lot of the ground in that area, once you see it, let me know. It has dropped on the chat box. Can we please go ahead? I will still send it to the class rep, but let's download it right away. Anif Amos, you should see it by now. It has left my own end. Your message came immediately after I released it. Please, let's be responding. If you can see the attachment. It has not dropped. Let me take it again. Let me take it again. I've resent it again. Be serious. Okay. Since you are not seeing it, I will send it to your class rep. Since you are there, you are not seeing it, I will send it to the class rep. Let me send it right away then. So the class rep will share it with you. Class rep, please let me check your WhatsApp. Though it's still loading. Class rep, by now you should have seen it. Check your WhatsApp. Confirm to me that you have seen it.
Yes, sir. I've seen it.
I've seen it, sir.
Okay, thank you. Now let's go to those who have questions. I hope the lecture of today is well understood before we close the chapter for today.
Yes,
No, you
sir.
don't, you may not see. Somebody is saying, Dixon, you say you have not seen it. Don't worry, I've sent it to your class reps WhatsApp page. They will share it with you. They will share it with you. Since you cannot see the one I'm sending through the chat box, they will share it with you. So as I was saying, so please put in your details and let me warn you that I have a way to know whether you just log in and you went your own way. I have a way to understand all these things. So it's not just enough for you to put on your camera or to put on your this thing without being part of it. On the account of this, please go and review what I've given to you. Problem set that we have given to you also is dealing with quite a number of other things with regard to that course, the topic that we have taught you. So I can assure you that you have enough materials that will be able to help you. I'm not giving you any slide, though. I'm not giving you any slide. Textbooks, I have recommended textbook at the beginning, and that's why I normally wait for you to jot. I won't give you any slide so that you can sit down and read through the notes you are making. At the beginning of this lecture, I said, have your lecture note as if you are in physical class. If you don't work by yourself, you won't understand it. So I'm not giving any slide to any student. That's why I take time. If I need you to write anything, I can wait as much as 5 minutes, 7 minutes for you to copy. So on the account of that, you can't have any note from me beyond what you are taking in your classroom. And that's why we have made the lecture interactive so that you can jot, you can work problems by yourself, and we can see if you are making mistake and we can correct you. Thank you. No note. So do have a wonderful time. Do have a wonderful time. So I'm closing the lecture for today. See you next week.
Thank you, sir.